So, chapter 4 homework is due on the 29th. The chapter 4 quiz will be on the 27th. That's Monday next week. It's not this week because David was out. Chapter 3 and 4 exam will be on the 29th. So the exam and the quiz for chapter 4 both got pushed back because David was going to be out. Gives you a little more time to study. The chapter 5 homework will be due on the 12th. We're starting chapter 5 today. So chapter 5 on temperature and heat. So temperature, when we talk about the temperature of something, we can talk about something being hot or cold, but these are really relative measures. You know, what qualifies as hot very much depends on the context. So, for example, in day-to-day life, 6,000 degrees, 3,000 degrees Kelvin would be hot. 3,000 degrees Celsius, that would be hot for your everyday life. But if you're talking about stars, that's a cold star. Then, the other extreme, when I was doing my research, 1 degree above absolute zero, when I was doing my research, that was the hot end of my measurements. The low end was at about 1/100th of a degree above absolute zero. But when 1 Kelvin is hot, that's a very different sort of situation. So hot or cold always depend on relative terms. But if we want an actual quantitative measurement, the thing we consider temperature is a measure of effectively the kinetic energy of the molecules of a substance. It's related to the average kinetic energy of the molecules of a substance. So how fast the molecules in it are jiggling or moving around. So it's a measure of the average kinetic energy of the molecules that make up something. The lower the temperature, the less the molecules are moving. The higher the temperature, the more the molecules are moving. And a thermometer is some instrument that uses the physical properties of materials to accurately determine temperature. So the original and the classic thermometers use expansion or contraction of a liquid. Like this thermometer on the wall here has a sealed chamber full of alcohol, which will expand and contract as the temperature changes, and then moves it up and down this capillary tube. That's how a thermometer works. You could use other properties. You could use, if you've got like an oven thermometer that's a dial thermometer, that uses the difference in expansion between two metals that causes something to bend. You can use electrical properties for various digital thermometers. So you can have a thermocouple or a thermistor. Those measure different electrical properties that are related to temperature. You could have, you can measure pressure and other things. There's a bunch of things. So the most common physically used property is for analog thermometers is thermal expansion. So the expansion and contraction of a metal or the expansion and contraction of mercury and alcohol. A dial thermometer uses the expansion and contraction of a metal. A liquid thermometer uses the expansion and contraction of either mercury or alcohol. Generally, they use alcohol these days. People don't use mercury thermometers very often anymore because mercury is nasty stuff. But I mean, there's a whole bunch of other things you can use to measure physical properties. So for like a dial thermometer, or if you have an analog thermostat, that uses a bimetallic strip, where you have a strip of metal of two metals stuck to each other, and one of them expands more than the other when heated. So here, if you have brass attached to iron, if it's straight at one temperature, when you heat it up, the brass will expand more than the iron and it will bend. And that bending will indicate the temperature. And you can twist one of these around into a coil and hook it to a needle, and it will effectively bend the needle very nicely. And then if it was colder, it would bend the other way. So like if you have an analog thermostat or dial type thermometer, these are all based on bimetallic strips. Coils of bimetallic material, because you can get a bigger movement by coiling it up, and thus it's easier to observe. Now, thermometers are calibrated to generally two reference points, the ice point and the steam point. Those are two of the common reference points. There are other things you can use depending on what temperature range you're measuring, but you calibrate them based on various known, physical properties. The ice point is the temperature of a mixture of pure ice and water at normal atmospheric pressure. That's 0 degrees Celsius. The steam point is the temperature at which pure water boils at normal atmospheric pressure. That's 100 degrees Celsius. Usually, a liquid and glass thermometer contains red or blue or green colored alcohol. Traditionally, it's been red. These days, I'm seeing more blue and greens, but it's just dye in alcohol. Or the classic ones were mercury thermometers, but people don't use mercury thermometers very much anymore because, again, mercury is not good for you. Now, there's 3 different temperature scales we're going to deal with in this class. Because we live in America, we use Fahrenheit. The rest of the world uses Celsius, and science uses the Kelvin scale. So conversion between Celsius and Kelvin is easy because the Celsius scale is named after Celsius, who invented it. Well, more or less. It's an improved version of his because his was weird and backwards. The boiling point of water was 0 and the freezing point of water was 100, which is weird and backwards. But so the Celsius scale is based off the scale of Celsius, where the freezing point of water is at 0 degrees Celsius, the boiling point of water is at 100 degrees Celsius. Normal body temperature ends up at 37 degrees Celsius. Room temperature is about 20 degrees Celsius. An absolute 0, the coldest temperature there is negative 273 degrees Celsius. Actually, it's negative 273.15, but we don't have to worry about the 0.15 in this class. Now, it turns out for science, it's really useful to have a temperature scale that starts at absolute 0. Because it turns out a whole bunch of physical properties are proportional to temperature starting from absolute 0. That corresponds basically to that kinetic energy. So Kelvin temperature is the Celsius scale. The degrees are the same size. There's still 100 degrees between freezing and boiling of water, but it starts at absolute 0. So 0 degrees Kelvin is at absolute 0. The freezing point of water is 273 degrees Kelvin. The boiling point of water is 373 degrees Kelvin. So to go from Celsius to Kelvin, you just add 273. To go from Kelvin to Celsius, you subtract 273. Very simple conversions. And then there's Fahrenheit. Fahrenheit created his system to somehow be better for weather. He decided that there should be 180 degrees between the freezing point of water and the boiling point of water and that the freezing point of water should be 32 degrees, and his zero was some mixture of ice and brine, and then there was something else based on the human body temperature, which is a terrible reference point because it's actually changing over time. The average human body temperature is changing over time, it turns out. We don't know exactly why, but people are getting colder. But yeah, so his system actually works better for weather, because it covers more of the range that you actually experience. But yeah, 0 degree, the freezing point of water is at 32 degrees Fahrenheit. The boiling point of water is at 212 degrees Fahrenheit. There are 180 degrees between freezing and boiling. Absolute zero, it is at minus 460 degrees Fahrenheit. Room temperature is 68 degrees Fahrenheit, to be equal with 20 degrees Celsius. And normal body temperature is 98.6 degrees Fahrenheit. Now let's go over how you will convert. So here are some standard locations. Absolute zero. Absolute zero is the coldest you can get. That is the point where there is no movement. You can't actually get there. You can get surprisingly close. I have personally cooled things down to 1/100th of a degree Celsius from absolute zero. But then my research was in low temperature physics, so and the lowest temperatures that have ever been achieved are like a nanokelvin. Nanokelvin. A few nanokelvin. But those temperatures, the number of things that are cooled, that's a handful of atoms being cooled. So temperature gets a little iffy. But it's totally possible to get down, to a millikelvin without on large-ish scales. I never got that low. I think we had equipment to get down to 5 millikelvin in theory, or lower, but I never needed to go that much. So, and our instrument was old and not always in the best shape. Tuning your dilution refrigerator to get that low is tricky, and you have to use secondary cooling solutions to get beyond like 5. Theoretically, the thing could have gotten down to 5. Don't think I ever got there though. So absolute zero is the coldest you can go. It's minus 460 degrees Fahrenheit, minus 273 degrees Celsius, and it is 0 degrees Kelvin. The ice point, the freezing point of water, is 32 degrees Celsius. 32 degrees Fahrenheit, 0 degrees Celsius, and 273 degrees Kelvin. And the steam point, the boiling point of water, is 212 degrees Fahrenheit, 100 degrees Celsius, and 373 degrees Kelvin. And the difference from boiling to ice is 180 in Fahrenheit and 100 in both Celsius and Kelvin. So let's go over how you do the conversions. To go from Celsius to Kelvin, you just add 273. To go from Kelvin to Celsius, you just subtract 273. Now to go from Celsius to Fahrenheit, you both have to change the size you are measuring, and you have to move your 0 point. So you multiply the temperature in Celsius by 1.8, and then you add 332 degrees, 32 degrees. I don't know why I was about to say 320. 32 degrees. So you multiply temperature in Celsius by 1.8, that's 9/5 if you're trying to remember it, and add 32 degrees. And that'll give you the temperature in Fahrenheit. To go from Fahrenheit to Celsius, you first subtract 32 and then you divide by 1.8. And that'll go from Fahrenheit to Celsius. The problem is that Fahrenheit and Celsius don't have the same zero. And to go from Kelvin to Fahrenheit or vice versa, I would generally suggest convert to Celsius first, then to the other one. I could sit down and work out what the actual formula for going from Kelvin to Fahrenheit is and vice versa, but yeah. So to convert a temperature, so the normal human body temperature is 98.6 degrees Fahrenheit. Let's convert this to Celsius. Temperature in Celsius is temperature in Fahrenheit minus 32 divided by 1.8. So 98.6 divided by 32, that gives us 66.6. We divide that by 1.8 and we get 37 degrees Celsius. So, Celsius plus 273, Celsius is Kelvin minus 273, temperature Fahrenheit is 1.8 times temperature Celsius plus 32. Temperature Celsius is temperature Fahrenheit minus 32 over 1.8. Here, let's convert the Celsius temperature of minus 40 degrees Celsius to Fahrenheit. So our formula is temperature Fahrenheit is 1.8 times temperature Celsius plus 32. And so that'll be 1.8 times negative 40, which is negative 72, plus 32 gives us negative 40. Turns out negative 40 is the temperature where both Fahrenheit and Celsius have the same temperature, same value. So here, convert 65 degrees Fahrenheit to Celsius. So temperature Celsius equals temperature Fahrenheit minus 32 divided by 1.8. So 65 minus 32 over 1.8, that's 33 over 1.8, which is 18.3 degrees Celsius. Let's convert negative 5 degrees Celsius to Fahrenheit. Give you a minute or two to work on that.
So temperature Fahrenheit is 1.8 times temperature Celsius plus 32. 1.8 times -5 plus 32. So that's -9 plus 32. That is 23 degrees Fahrenheit. Here, let's convert 77 degrees Kelvin, which is the temperature of liquid nitrogen at atmospheric pressure, to Celsius. So if you have like a tank of liquid nitrogen, that's the temperature it'll be at. Usually. So this is a conversion from Kelvin to Celsius, so it's very easy. Temperature Celsius is temperature Kelvin minus 273. So 77 minus 273 is minus 196 degrees Celsius. Let's convert 100 degrees Celsius to Kelvin. This is just the same thing, but in the other direction. We'll add 273. So 100 plus 273 is 373 Kelvin. And so for degrees Fahrenheit and degrees Celsius, you do need the degree symbol. It's actually optional with Kelvin. You can just use a K. And you definitely need it for degrees Fahrenheit and degrees Celsius because a capital C and a capital F are different units. They're electrical units, but they are existing units.
So here, this is 4.2 degrees Kelvin. Let's convert it to Fahrenheit. This is the temperature of liquid helium at atmospheric pressure. You can make it colder by pumping on it. So for this, we're going to do 2 steps. First, we'll convert to Celsius, then we'll convert to Fahrenheit. So temperature Celsius is temperature Kelvin minus 273. Temperature Celsius is 4.2 minus 273. That's minus 268.8 degrees Celsius. Temperature Fahrenheit is going to be 1.8 times temperature Celsius plus 32. So 1.8 times minus 268.8 degrees plus 32 is minus 483.84 plus 32, which is minus 451.84 degrees Fahrenheit, which would round to minus 452 degrees Fahrenheit. Now, the correct formula to go directly to Fahrenheit would be temperature Fahrenheit is 1.8 times temperature Kelvin minus 460 degrees, I believe. Let me check if that gives me the same answer. Rounded to the nearest degree. So 1.8 times 4.2 minus 460. That also gives me 452. There's a difference in there, but that's because there's some rounding to generate that. So I would generally do the conversion here. But yes, you could do a direct conversion, and you would the other one would be temperature Kelvin would be temperature Fahrenheit plus 460 divided by 100. And there are other temperature scales out there. There's a equivalent absolute temperature scale like Kelvin for Fahrenheit. It's called like Rankine scale or something. Really only used by certain engineers. So let's do 70 degrees Fahrenheit to Kelvin. And we'll do it in 2 steps. So temperature Celsius is temperature Fahrenheit minus 32 over 1.8. So 70 minus 32 divided by 1.8, 38 divided by 1.8, that's 21.1 degrees Celsius. And then we add 273 degrees. 21.1 plus 273 is 294.1 degrees Kelvin, or 294 Kelvin. And if I did it with my direct formula, 70 plus 460 divided by 1.8, I would also get 294. So we talked about temperature. Temperature is this jiggling motion of the average kinetic energy of particular atoms. But there's also potential energy. There's kinetic and potential energy. They both exist at the molecular level. So kinetic energy is the motion of molecules. Potential energy are the bonds that result in the molecules oscillating back and forth. And this kinetic energy, that average kinetic energy for heat, is a little complicated. You could have things, but it's sort of the average, like bouncing around kinetic energy. If you have energy in spinning and stuff, that sort of gives extra storage for heat. So heat is energy that's transferred from one object to another as a result of a temperature difference. Heat flows naturally from high temperature to low temperature. You can make heat flow from low temperature to high temperature, but you need something to make it move. Use a pump, a heat pump. Or, an air conditioner. An air conditioner is a thing that moves heat from high temperature to low temperature. A refrigerator does the same thing. Pulls heat out of a low temperature reservoir and puts it in a high temperature reservoir. Yeah, sorry. So an air conditioner does the opposite. It moves heat from low temperature to high temperature. But heat is energy in transit because of a temperature difference. Often we'll talk about heat like stored in something or heat in something. Technically, that's like internal energy or thermal energy internal. It's just often more convenient to talk about it as there's some heat in the substance. But heat is technically the energy in motion. It's like the difference between work and energy. Heat is, work is the other thing that you can have involved in this. So, work is energy from a force. Heat is that thermal energy moving around. Since heat is energy, its natural unit would be joules, because it's energy. However, we didn't know heat was energy for a very long time. So we have a whole set of units to measure heat that are not based on the fact that it is energy. So a more common unit to measure heat is the calorie. So the calorie is the amount of heat necessary to raise 1 gram of pure water by 1 degree Celsius at normal atmospheric pressure. So 1 calorie is about 4.2 joules. It's 4.186 or 184. I don't know. I've seen different conversions. That's 4.186 joules in the book, I think. And a kilocalorie is 1,000 calories. That's what kilo means. That's the heat necessary to raise 1 kilogram of water by 1 degree Celsius. It is also the calories on food labels. Calories with a capital C on food labels are actually kilocalories. And sometimes on European products, you will see them actually labeled as kcals. But in America, they're calorie with a capital C. I will call them food calories whenever I talk about them in this class. Those are kilocalories, 1,000 calories each. So 1 food calorie is 4,186 joules, or about 4.2 kilojoules. And this is the heat required. A calorie is, a kilocalorie is the heat required to warm 1 kilogram of water by 1 degree Celsius. There's also the British thermal unit, which you will run into on heating and cooling systems. So like your furnace or your air conditioner in the US. And they're usually rated in BTUs per hour. Though often it just says BTUs. They leave off the per hour. But a British thermal unit is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. It is about 1,055 joules, or about a quarter of a kilocalorie, or 0.00029 kilowatt hours. So air conditioning units and furnaces tend to be rated in BTUs per hour. Heating units are generally rated in number of BTUs supplied per hour. Air conditioning units, BTUs removed per hour. I've also seen it on gas stove burners, rating BTUs per hour. So knowing that 1 food calorie is 4,186 joules, how many joules of energy are in a 300 food calorie can burger? which is in fact the number of calories in a McDonald's cheeseburger. So this is just a unit conversion. 300 food calories times 1,000 calories per food calorie times 4.186 joules per calorie. So 300 times 4,186 joules per calorie per food calorie. This is 300,000 regular calories times 4.186 joules per calorie is 1,255,800 joules, or 1.26 times 10 to the 6 joules. 1.26 million joules, or 1.26 megajoules. If I had 300 calories of heat to 100 grams of water, how much will the temperature go up? Remember that 1 calorie raises 1 gram of water by 1 degree Celsius. So 300 calories distributed over 100 grams. So for every gram of water, it gets 3 calories. 300 calories divided by 100 grams times 1 degree Celsius gram per calorie. It will go up by 3 degrees Celsius. 300 calories, each gram of water gets 3 calories because there's 100 grams to spread it out over. Each calorie raises the temperature of 1 gram of water by 1 degree Celsius. If on a brisk walk, a person burns about 325 food calories per hour. If 1 pound of body fat stores 3,500 food calories, how long would it take to burn 1 pound of fat by walking? So time is going to be, we have 1 pound of fat is 3,500 calories per pound of fat, and it takes 325 calories per hour to burn off fat. So we have 3,500 calories divided by 325 calories per hour, and we get 10.8 hours. kind of ridiculous amount of time. If I burn a 250 food calorie candy bar to heat 4 kilograms of water, starting at 0 degrees Celsius, what temperature will the water be when all the candy is burned? So, assuming all the heat from the 250 food calorie candy bar goes into the water, what temperature will it be? So here, 250 food calories is 250 kilocalories. The change in temperature is going to be the heat over the mass times 1 degree Celsius kilogram per kilocalorie. We'll take 250 food calories. We're spreading it out among 4 kilograms of 250 kilocalories spread out among 4 kilograms of water. And that'll tell us how many degrees our temperature goes up by. It'll go up by 62.5 degrees Celsius. We started at 0 degrees Celsius, so our final temperature will be 62.5 degrees Celsius. We'll go into how this fully works a little later when we start about specific heat. If I burn a fuel pellet to warm 3 kilograms of water from 10 degrees to 60 degrees Celsius, how much energy is in the fuel pellet in calories? So for this, 3 kilograms of water going up 50 degrees Celsius. So our change in temperature is 50 degrees Celsius. So our energy is going to be 50 degrees Celsius times the 3 kilograms of water times 1 calorie per degree Celsius gram. So we'll convert 3 kilograms to 3,000 grams, multiply through, and we'll get 150,000 calories or 150 kilocalories. So let's talk about expansion and contraction with changes in temperature. So for most substances, when they warm up, they get bigger. When they cool down, they shrink. So in general, most matter, solids, liquids, and gases, all expand with increasing temperature and contract with decreasing temperature. There's one big exception to this rule: water. Below 4 degrees Celsius, liquid water will expand until it becomes solid ice as you cool it. So water expands as it cools below a certain temperature. Ice floats. So water is a big exception to this. But the fact that things expand and contract with temperature is something we have to take into account. You've probably seen these joints in bridges. Those are they're often covered with like zigzaggy rubber sheet or something like that, so that if they allow for the expansion and contraction of the bridge. Because the bridge isn't on the ground, it'll heat up and cool down faster than the road that's on the ground or the ground around it. And that means it can expand and contract more than what it's set into. And so you don't want it to expand and buckle or contract and cause problems. And this helps prevent that. So this allows contraction and expansion of the steel girders during the winter and summer seasons, and keeps the road, your bridge from expanding too much and like kinking and buckling, which would be bad. Now, water is strange. Water reaches its most dense point at about 4 degrees Celsius. And then as it cools, it expands. This leads to some really weird things where if you have a lot of water that's all piled up and the cold water sinks and the warm water rises, the bottom will be 4 degrees Celsius and it'll stay there. And if it gets colder, it will rise up and mix with the water above. So this has some really interesting effects. So below 4 degrees Celsius, the volume increases slightly until you get ice. And with a minimum volume at 4 degrees Celsius, the density of water is maximum at this temperature, and it decreases at lower temperatures. And the real thing that's important about this is this causes things like bodies of water freeze from the top down, because ice floats. Which means you preserve an area that's still liquid below, at the bottom of a body of water. And this can keep living things alive, for example. So ice has this structure, this hexagonal structure, and it takes up more volume than liquid water. Because liquid water jiggles around more, it's not as tightly bound to other things. It can sort of slide into the gaps here. So ice will have this open hexagonal molecular structure of ice. You can see this with snowflakes. They form this hexagonal, you get this hexagonal patterns because of the hexagonal structure of ice. And because of this, lakes will freeze from the top down because ice will flow. So this is Yellowstone Lake freezing from the top down. So we talked about expansion and contraction. In general, things expand when you heat them and shrink when you cool them. So if I have a tight iron ring, I'm trying to put around a wagon wheel to use as a tire. To put it on easily, should I heat my ring or should I cool my ring? What do you think? Should I heat it or cool it? Yep, because when you heat it up, it expands. So often if you're trying to get things unstuck, so if you're trying to like seat like something into a tightly fitting hole, you often heat where the hole is so the hole expands, and you can cool the thing you're putting down. So if you guys, there's some tricks for installing bearings and stuff where you cool the bearing and heat where you're putting the bearing. But for iron rings, this is actually how you put tires on wagon wheels traditionally. Your iron tire is actually slightly smaller than the wagon wheel. You heat it up, and then it contracts around the wagon wheel and holds the wagon wheel together tightly, as you can see here in this video.
Exactly. Yeah, no, it's quick stuff.
Here's an example.
And I
have the wooden wagon wheel there.
polar bear.
Oh. And I have the tire in the fire. No.
Growing about 10. So we've got 85 and 7/8, 86 inches. 86 times 10 is 860, which is 7/8 of an inch. And we only need 3/8. So the circumference should be half an inch more than we need if the tire is as hot as that bar. I've got that bar right in the coals. Yeah. Chances are it's not as, the tire's not as hot.
I think it has to be long enough for not
Well, for me anyway. I'm a fire hazard. Not so much for Gary.
I'm okay.
Sitting flat.
Oh, okay.
The spokes are a little wider than the fellows, and the other thing is these little clips you see are sticking down.
Right. So you're going to remove them once you put the wheel on?
The tire will go right down to here.
Okay.
The tire is the same width as this. So.
Right.
So the tire will cover the whole wheel. If you didn't have a little piece of metal in there, it wouldn't cover the whole wheel maybe.
Okay, it would stick out on the top.
Yeah. Try it down. That's not going to come.
Fire light? Fizzle them a little bit, so if we can start it there, get it on that one.
Yep.
Hammer's there.
Okay.
I can get this.
Okay.
Okay, yeah. Get the hammer.
You can see it's loose-ish. I mean, it's a stub fit. It goes down. And now when you cool it down with the water, it's going to trim.
Now just watch this crack right here, how it comes up. Right here. It'll come in. If it's not smoking, there's a spot where it's smoking a little bit there. Mostly that's the linseed oil smoking.
You should have Carl over here, the Swiss for great wheelwrights. He likely did this in his childhood over there.
What? You'd be more propellers, would you?
What's that?
The Swiss, the propellers. The ship.
I don't have many ships in Switzerland, is there?
I don't think you're handy at
wood
this, Boone. I think you've
burning.
been doing it before.
Oh, yeah, but you had 5, didn't you, at Lindsay?
Yeah, you did 5 in Lindsay.
Yeah.
And you did 1 or 2 at my shop.
Still warm? Yeah.
Oh yeah.
Oh yeah.
You can really see the gas blowing. Oh yeah, you can, hey?
It'll come in. Spot there.
So what are you working on at St. Marie?
We're conserving
You know, the oil is something you
Oh,
could
okay.
bring up from
Somebody
Lindsay.
asked me. I said it's like the fireplace.
Keep the
Yeah,
oil
there's a
from
lot of
Lindsay.
other stonework over
Could you
there.
bring that
but-
from
No, I mean, that's
Lindsay
the,
down
that's all the stonework.
I don't know if you even named it. There's no stone foundation.
No, I think it's from Calvin.
Only for the bastions, but,
Oh,
yeah, we're working on the ruins. In the 60s, they put a bunch of Portland cement on there.
Why would they need that in?
No, I thought they were doing well, but I don't know. They did a lot of crap. at
Oh,
the
there's a few
there.
things that happened at that
How
time.
did you get, that's all you need? That's all you need, the steel touching?
Yeah,
the
just as
water,
long as the
so
steel's
cup
in,
the-
so.
cup the water to get, if you like.
There you go. So, here, if I have a steel nut and bolted stuff, if I heat the nut and bolt, will it be easier or harder to remove the nut? I'm heating both of them. And I'm gonna, and here, I'm assuming they're made of the same material. Do you think it would be easier or harder to remove the nut if I heat them? You're heating both of them. Well, you might think that because the bolt will expand, the nut will also expand. And what will happen is actually the gap between them will expand because they're both expanding at the same rate. So any hole they had will get bigger. So it will should, in theory, become easy. Now that's assuming they're heated at the same to the same temperature. If I hit the nut and bolt, they'll both expand, but they're made of the same materials. This should also expand the gap between them, so they should expand at the same rate. This is if they're made of the same materials. It gets a lot more complicated if they're not made of the same material. And I think that is it for today. We'll stop there. Any questions about any of this? We'll continue this on Wednesday. And you'll have your quiz on chapter 4 and the test on chapter 3 and 4 next week.